So we had started with this picture. This is a circle with radius 1, so it's the unit circle. And I'm calling this angle x. And we're thinking about the situation as x is approaching 0. So geometrically, you can imagine this line slowly approaching the x-axis here. I said that we should start by setting up a sandwich and then try and get the algebra to fit the problem that we're trying to solve. So if you remember the idea of the sandwich theorem, it's that there is one function that's always larger than the function you care about, that's the upper bound, and there's another function that's always smaller than the function you care about, which is the lower bound. So if we're thinking like very sort of vaguely, you have a sandwich whenever you have three quantities that are always in increasing order. So I'm looking for, in this picture, what are some lengths or some areas or some other quantities where one is always between two others, because that's got a sandwiching kind of a feel. So one thing I'm noticing is the small triangle here. Let's do it in terms of areas. The area of the small triangle here always looks like it's going to be less than or equal to the area of this sector here, and that's always less than or equal to the area of this larger triangle here. So that would be one possible sandwich. Another possible sandwich is, let's just pick off some lengths. So this length of that triangle looks like it's going to be smaller than that arc, which is smaller than this leg. So just that piece is going to be smaller than the arc is smaller than the big leg. Okay, let's do the one we did in class, which was the one in terms of distances. So I want to write some algebraic expressions that let me describe each of those lengths. So we know that because the hypotenuse of this right triangle is 1, because it's the unit circle and the radius here is 1, SOHCAHTOA tells me that the length here is just sine of x, because sine of x is going to be that length divided by 1. So here I've got, by the way, this isn't a 1, that's supposed to be the side of the triangle. Alright, so I've got sine x is that length, and then I need to figure out this arc, and a lot of people had trouble figuring out what was the arc length there, and we'll come back to that. And then this one, again, if I use SOHCAHTOA, I've got that is length 1 because it's a radius. So tangent of x is this height divided by 1, which means the height is just the tangent of x. Okay, what happens if you forgot the arc length formula? Very easy to find it out again. So let's think about, here's an angle x, we want to know what's that arc length. Let's think about this arc length as being a certain percentage of the full circumference. So if my radius is 1, the full circumference is just 2 pi. Okay, so what percentage of that 2 pi do I want? It's whatever percent this little slice is. So let's look at what percent of a full circle this angle is. So if I have my angle x divided by, let's see, a full circle is 360 degrees, which is the same thing as 2 pi radians. It's like this is now the percent that my angle is of a full circle. And I'm going to take that percent and multiply it by the circumference, and we get x. So we get that arc length is just x, which was surprising to a lot of people, but that's how radians were invented. Radians were invented exactly so that the arc length of the unit circle would be equal to the angle measure there. Okay, so now we've got our sandwich. We've got that this small length here, sine x, is less than or equal to the arc length x, and that's less than or equal to this distance, which was tan x. So now I said we've got to sort of force our will on the algebra. If we're going to be able to apply the squeeze theorem here, we want the function in the center to be sine x over x. So let's do some algebra to make it that way. Lots of people were saying, well, here we see a sine x in the denominator, so maybe let's try and get this x to be in the denominator. So what they did was they took the reciprocal of all three parts here. So now that's 1 over x, and now that's 1 over tangent x, which is the same thing as cotangent x. I don't know if you noticed, but all of the inequalities reverse direction here. I think it would be nice algebraically to justify for yourself that that needs to happen, but kind of intuitively it makes sense. If you think about sine x as being some number that's smaller than another number, when those are in the denominator, it's like if you've got a smaller denominator than this one, then the overall value should be larger than this one. So that's kind of an intuitive explanation for why the inequality should reverse there. And now all I need to do to get the sine x in there is I'll multiply through by x on all sides. So I'll multiply through by sine x on all sides. So when I multiply by sine x, that becomes 1. This becomes what I was hoping, sine x over x. And this becomes sine x over, well, okay, let's write tangent x. So tangent x is sine x over cosine x. And so we can reverse and multiply, and the signs will cancel. So this is really the same thing as cosine x. Great. So now we've got the first ingredient for the squeeze theorem argument. We have that 1 is greater than or equal to our function, and our function is greater than or equal to cosine x. The second thing we need to show is that the limit of the upper and the lower bound both approach the same value. So limit x approaches 0 of 1 is clearly 1. Limit x approaches 0 of cosine x is also clearly 1 because cosine is a continuous function, so there's no problem. You can just evaluate it directly at 0 by plugging it in. So because both of those are true, we can conclude by the squeeze theorem that the limit as x approaches 0 of sine x over x is also 1. And it's very easy to see graphically, if you want to see it graphically. Let's take a quick look at that. Here's sine x over x. Here's the function y equals 1, which is the upper bound. Here's the function y equals cosine x, which is the lower bound. And you can see the sandwich happening. You can see from the right-hand limit here, as x is approaching 0 from the positive direction, both the upper and lower bound, the limit is approaching 1. And that's squeezing our function so that its limit as x approaches 0 is also equal to 1. Hope this was helpful. I'll see